It is a great honor to be here today, to stand in front of you and just receive a medal, gold medal of this famous university from the rector of your university. Let me also thank the Vice Rector with his fine words of introduction. Let me congratulate the Comenius University with their 100-year celebration, their birthday 100 years ago, and our friendship and cooperation, because I realize among the classical universities of Europe, Groningen, Comenius University, several others, we have established cooperation and friendship, and it is a real pleasure, I must say, that for many years we had intense contacts. Professor Radovan Sebesta, who is in the chemistry department, he was in my group several years ago. We have exchanged students. Currently, we just hired a young person from your country as a faculty member in our institute. We just had a student, this summer from the science department here. We will exchange students and we will cooperate a lot more in the future. I look forward to that. So once again, thank you very much, and also for organizing this beautiful journey for me and my wife to your country, and I will go to the Tatras to the chemistry symposium later today. Thanks to Professor Milata and Omastava for organizing everything and make our stay so pleasant. Thank you so much. So what I want to do is to talk a little bit about the joy of discovery and explain to you a little bit what we did in the field of nanotechnology. And don't worry, I'm a chemist, there will be no exam afterwards. So, indeed, it was mentioned before, universities should be playgrounds. Yes, we are very serious, of course, at universities, because we train the next generation of students. We try to get new insights, knowledge, science, discoveries in all disciplines. But indeed, we need also to value that we are a playground for discovery, for insights, for bringing ourselves to the future. Not in isolation, but together with our partners in industry, in society. So, when we go the path to the future, through this beautiful garden, which is called the Garden of Knowledge, we go for challenges for our youth, dreams for the people, and opportunities for society and industry. It is an adventure in the future, ladies and gentlemen. And we admire the beauty of knowledge and science, but often we get lost. We got completely lost in this beautiful garden because we are not on the right track. We simply have not the right knowledge. We have to invent and find out. But then, we should not forget, asking the right questions is what is the most important we should do at our schools of education. And often we hit upon questions here that we have never thought about, and these are often the most interesting questions because they bring breakthroughs and advances in our knowledge and understanding. And we should not forget to enjoy the beauty of the scientific world. So it was indeed mentioned, the Wright brothers. I often get the question, why do we need nanomachines and motors at nanoscale dimensions? This same question was more or less asked to the Wright brothers slightly over 100 years ago. Why do we need airplanes? If God wanted us to fly, He would have given us wings. But don't forget, nobody had predicted that 100 years later we would have the Airbuses built in Europe that can carry 400 people across the ocean. At 1,000 kilometers an hour, several thousand miles across the ocean. We admire the flying pigeon. But try to fly 400 people at 1,000 kilometers an hour across the ocean, you will completely fail. The beauty of the pigeon is not directly translated into a plane. All the components here, the 3.5 million components of such an airplane, are completely artificial, built by chemists, physics, material scientists, engineers, computer scientists, etc., etc. And the flying principle of a Boeing, ladies and gentlemen, is not the flying principle of the pigeon. We admire Mother Nature, But we should never forget that it starts often with very fundamental questions. I suppose you all have a smartphone. Don't forget, how did fundamental science bring us to a modern society? Which were the fundamental scientific questions to be asked and new insights and discoveries? Many young people don't realize that it was more than 50 years ago that chemists made the first liquid crystal materials for the displays, and that the physics discovered the transistors, yes, in the late 40s and early 50s of the past century. And together with our engineers, the computer scientists, and many other groups, we were able in our industries to develop, of course, smartphones. And the smartphone only is there for 12, 13 years. And it completely changed our society at every level. We agree, I think, all on that. I know there are prominent figures from information technology and companies here. We really admire how far you bring this forward. So, I'm a chemist, and facing our future, we know chemistry is everywhere. We have to think about sustainable processes in our future, or how to reinvent materials, to make them cleaner, to make them cost less energy, to recycle materials, etc. Change the face of the chemical industry, lower energy, or make drugs not only by trial and error, but making better pharmaceuticals that suit you or you precisely. So chemistry is a creating science par excellence. But it's also asking fundamental questions and then offers challenging perspectives for industry. So the joy of discovery, ladies and gentlemen, started with me when I was a small boy. Look, this was when I entered high school. And I was the second of a family of 10 children. These were my parents. I grew up on a farm in a remote village on the German border in the northeast part of the country. But at a very early age, and also thanks to my parents, I started to admire the beautiful colors in the fields and how a garden could grow from a tiny seed. And we were asking questions. And there was, of course, a great playground. Yes? And then I went to high school, and I had a fantastic chemistry teacher, op de weg. And he knew his topic. He challenged us. But he also wanted to give us perspectives. Why it was important to do mathematics. Why to solve a difficult formula. Or to do physics. Or to study chemistry or biology. And I still own a lot to that today. And I'm sure you all remember that one teacher in your schools that made the difference. Then I went to the university. This was Professor Winberg. He had a background in American education. He challenged us a lot. This was my first molecule that I ever made. I was 20 years old. That was the first new molecule. And I came to Winberg's office, my professor, and he said, that is fantastic. Nobody made this molecule in the world. But it's absolutely useless. But can you imagine how proud I was? It's like making your first song, your first piece of art, yes, your first poem. So I want to give credit to the teachers at all levels because they shape the future with our young talents. And we should never forget that. So in the art of building small, we do chemical synthesis, like so many colleagues here, and we develop a passion for molecules and design a molecular world. So building molecules because we simply think we have to test the theory. Or we want to build a molecule, a material for something useful, being a new medicine. Or simply because it's a beautiful molecule. So building molecules and materials in the laboratory with our students, the undergraduate and the graduate students, the PhDs, the postdocs, we share a universal language around the world. I'm not speaking your language, but I can discuss with every chemist here, a physics person or biology, because we have the universal language of molecules and the atoms, thanks to the periodic table. We have no borders. We go beyond frontiers. That is the goal of a university, to bring our students further. We share international cooperation, and we have a passion for discovery. So being a chemist, we realize we should not forget that we can make small molecules like ethylene, the basic for many of the plastics, like your plastic bag, 160 million tons a year. We can discuss later about the problems with plastic and recycling. We can make very complex molecules like vitamin B12. Look, carbon, hydrogen, nitrogen, oxygen, phosphor. Vitamin B12 was called the Mount Everest of synthetic chemistry when it was made for the first time by Woodward and Hashimoto. Very complex, very simple. Here we produce only 35 tons a year in the whole world because you need only micrograms of vitamin B12 to keep yourself healthy. Very essential for the world. Complex and simple. So we make the cables and the cars, all the components, including the fuels, the soaps, the dyes, the drugs, the pharmaceuticals, all the components of your smartphone. This is what we can do. And we should be a bit proud. Of course there are problems, you know, with technology and recycling and all these things. And dangerous waste, we should avoid that. But what we are not good at is making anything that moves. When you lift your arm, when I speak to you, when I walk, biology, living objects move. And this is what you find in your body. The rotary motor, the bio-nanomotors that make things transport in your cells. You see here, like on the roads, like on the highways. The ribosome, which is a robot which generates all the proteins in your body, a fantastic machinery. Look at the bacteria, how it swims in your guts with this fantastic motor. It can go where it needs and finds food. Or the optical switching, the process in your eye. This is molecular nanotechnology in your body, working very hard. Millions and billions of machines at this moment. So, this all started with Richard Feynman. The name was mentioned before, in 1959 when he said there is plenty of room at the bottom. That means go to the level of atoms and molecules, like in Mother Nature, and build from there. And this was the first computer. It was half this room, and it could do way less than your smartphone. But now we are down to 12 nanometers or so in the newest chip technology. Going down. But what we want to do and what the chemical community and material science typically do is building up, bottom up, like Mother Nature does it, starting with atoms and small molecules and building all these beautiful things. And it was 50 years later that I had the privilege to go with Sir Fraser Stoddart and Jean-Pierre Sauvage to Stockholm, because we built some molecular motors and machines. Just to remind you, for those people who are not in the natural sciences, nanotechnology, 1 nanometer is 1 billionth of a meter. So your hair, if I take one hair here, you see, this is one hair, the cross-section of your hair is 80,000 nanometer. 80,000 nanometer, it's really huge. And does size matter? Yes, of course, we all know that. When you go to a pebble beach or you go to a beautiful sandy beach, yeah, it feels perfectly different, eh? You know that. It's the same material. Size matters. So where do we find nano at the moment? Nanoparticles, for instance, in these high-sensitive, nanosensitive creams, you know. It's also a bit expensive, eh? But the tiny particles, it feels really good, I tell you. You have the quantum dots, you see 6 nanometer and 2 nanometer, you get this high definition LCD screens. So all kinds of properties depend upon size. But this is hard particles, and the people from the inorganic materials community know this. The particle size, these are hard materials. But in your body, it's all soft materials, except for your bones. So how to build machines from soft materials? And this is what I'll focus on. And I will start with switches. You all know what a switch is. Switching on, off, 0, 1, 0, 1. And so the most beautiful switch is in your eye. The fact that I can see you and you can see me is due to a molecular switch. Just like you switch on the light here, or I switch on my laptop. This molecule, called retinol, is a band molecule. This is more linear. And what you do is, when light comes to your eye, you switch between 2 states. A band state and a more linear state. And that gives a signal to your brain. And we thought 30 years ago, wouldn't it be great if we could do molecular computing and information storage like in your eye? Building molecular switches that you can switch with light. Not electronics, but with light. This is how we started. And we built switches. You might say, why don't you take the components from that Mother Nature gave you, from your eye? But you realize you cannot build a computer with your eye. The materials are way too sensitive. So we built all kinds of switches. The structure is not so important. We built artificial switches, and we could make then information storage at the molecular level. And to give you an impression, when you go down to the level of 1 billionth of a meter, and you build a switch, you can make 0101 information storage. You can make a compact disk or electronic devices, and you can make one compact disc and store this megabytes, which is 240 years of music on one compact disc. Can you imagine? Your grandparents and your grandchildren, 6 generations, use one compact disc and can play music for 240 years. This is not reality yet, but we can switch. I will show you one more example of a switch that we recently developed, because we work a lot together with the medical school and with biology people to make smart drugs. We all know when we take a medicine, we like to have a medicine that does something. Otherwise, you don't take a medicine. Then you don't like your doctor, if it doesn't work. We want to have smart medicines that we can switch on and off exactly on the spot with a flash of light. So you have an infection here or a tumor. You take this drug, it doesn't harm anything in your body except where you put your light, your laser or whatever, and you switch it on. This is the dream. Smart therapeutics, precision therapy. This is the future. And we have a big program, and many groups in the world work on that now. We work on bacterial resistance. It was called by the World Health Organization one of humanity's ticking time bombs. Cancer treatment. We all know the problems with chemotherapy and all these tumors, small tumors that are difficult to detect. But once you detect, how to treat them without losing your hair and getting all the other side effects. So here I show you one example. This is Cipro, which is an antibiotic in the clinic. And we build in a light switch, and we can switch on and off the antibiotic. So we switch it on, it does its job. 24 hours it gets in the environment, it's off. It does not build up resistance. High precision therapy. You can see we can even grow bacteria in this yin-yang figure, just using a mask where you irradiate or where there's no light. That is a bit of my dream for the future. Starting from the eye, building information storage or smart drugs, not now, but in the future. Let me move on to motors. We all know what a motor is. A motor in your car, yeah? The fact that we can move, that this animal can crawl, that this plant can move towards the sun. There are motors and machines in biology everywhere. Remind you again of the bacteria. What is the most beautiful motor that I know? You might think of your car, Depends on which car you have, of course. But yes, in a Ferrari there is a fantastic motor. This is the most beautiful motor that I'm aware of. This is the ATPase rotary motor in your body. It generates ATP, the fuel in your body. And I don't know if you ever realized that this is a few nanometers in size. It rotates, It rotates, you see? Things go in and out. It produces the fuel. You know how much? Half your body weight. Can you imagine? You are 80 kilograms. It produces almost 40 kilograms every day. Almost half your body weight every day. Not one motor, Billions of these motors at this moment in your body. Now, you don't eat 40 kilograms. I don't eat 40 kilograms a day. It is most of the components are recycled. So if people talk about one of the big challenges for the future, recycling of our materials, why can we not do it? We are just not smart. We have to learn how to invent these things. Our body does it all the time, every day. So what is the problem? What were the fundamental scientific questions that we were facing? Of course, how to control rotary motion. And you have to put energy in, otherwise it stops, no rotation. But how also to control left or right. Imagine you are in your car, and there is equal probability going backward and forward. You know what happens? You will not go anywhere. You either go right or you go left. How to distinguish at the nano scale, at the molecular scale? We all know about mirror images, left hand and right hand. This is the most beautiful example, the right-handed helix of DNA. It was called the Mona Lisa of modern science. And I think we all agree on that. So what we did is we built tiny motors, less than 1 nanometer, 1 billionth of a meter in size, that have either right-handed form or a left-handed form. And we put in light, like in your eye. The energy comes from the light. And then it can spin. And this is the tiniest motor in the world. 1 nanometer in size, powered by light. And you see it spins in one direction. This is the world's first nanomotor. Of course, afterwards we built many. And you might ask me the question, how fast is this motor? The original one that we developed in 1999 rotates once every hour. Now you cannot build a car with that, if it goes only once an hour. But now we have motors that rotate once a minute, once a second. Even the fastest one goes 10 million times per second. So you can design exactly how fast they go for different purposes. So yes, we can rotate. You can see we can have objects rotating. This is an object you can see with the bare eye. You can see here a tiny spider, and it moves. Rotation and translational movement. I don't touch this. This is just taken in the laboratories, and it moves. This was an eureka moment in my whole journey. The joy of discovery. Can you imagine? On a Tuesday afternoon at 5:15, students came to me and said, "Professor, you have to come to the lab. We want to show you something." And they showed me this object rotating. I could see it with the naked eye just by switching on the lamp. Can you imagine the breakthrough? You see something autonomous moving that you designed in the laboratory without help, and it moves. I could not speak for 5 minutes. So we, as a good Dutchman, we built a windmill park. So we built tiny, this is what our ancestors built 500 years ago. You can still see them when you visit our country. We built them 1 billion times smaller. These tiny windmills that spin are on the, in this case, on a gold surface. And you might say, like was mentioned before, what are these professors and students at universities do? Are they just playing like in kindergarten or so? Playing with Lego? Yes, maybe sometimes. We wanted to see if we could have these motors rotating and spinning. Because now suddenly we have a surface that is dynamic. And look, people now think about self-cleaning windows. And in China, the first self-cleaning windows are prepared now. Not based on our motors, but once you know how to do it, once you know the principles, you can have surfaces that move, that can clean themselves. Solar panels. Now this night it was raining heavily here, so your solar panels are fine, they are cleaned. But when you go to south of Spain or to the Sahara or to California, there's a lot of problems with these solar panels because there's dust all the time and the efficiency goes down. Can you imagine? It moves with the sun and the sand goes off and it cleans itself. Your car is cleaning, you don't have to wash anymore. The materials repair themselves. These are hot topics in science around the world now. Dynamic functions. Self-cleaning walls, self-cleaning windows. We also built a molecular car. Why did we do that? Now, my students were a little bit jealous of these students of the engineering schools that go and build these. For instance, the students have now this car race in Australia. It's always in September. They go through the desert with these electrically powered, solar-powered cars. And my students were very jealous. And they said, can we also, Professor, can we go to Australia? And I said, no, we are not engineers. We are molecular engineers. So let's build a molecular car. So you see, 2 meters, 2 nanometers. It's a 4-wheel drive. It's a little bit smaller. And it took us 8 to 10 years to build it, to see if we could move something. It was, of course, not of building a car. The scientific question was, can we go from rotation, a rotating motor, to translation, to move something forward, to transport something? And yes, we built it. Here it is. And now I have to give a warning. In your body, ladies and gentlemen, when you move your muscles, it's a bit different movements than the movement of the car in the street. This is more realistic at the nanoscale. If the movie works, I can show you. So it walks over the surface. This is nanoscience. So this is how our car moves. And to make sure that you understand that I'm not telling jokes, I borrowed this from Harvard. Ladies and gentlemen, this is happening now in your body, in your cells. The highway, the motorway is built from the proteins, you see? And when the car has gone by, it breaks down and a new motorway is built. It's all dynamic. This is nanotechnology in your body, with small molecules, with proteins. And you show you in a moment how things are transported. Look, this is how things are transported in your body, in your cells, at a giant pace. This is 1 billionth of a meter in size. Yes, ladies and gentlemen, inside your cells, in your body, millions and millions of these machines. So, we all know what a modern electric car is and looks like. And you probably will, most of you will own an electric car in the future. This is our nano car. This tiny white powder. 1, 2 meters. This is, you see, our car. But we built, in the typical chemical process, 1 billion times 1 billion identical nano cars. That's in this tiny flask. So I would say our car manufacturing plant is not so bad after all. I come to a conclusion, but not before I want to give you a small perspective to the future. Will we have nano robots that go through your blood veins to deliver a drug, to detect a tumor cell, to do a repair in the future, guided by our computers, by our information technology? Nanoscience in our medical schools? Yes, I think so. It looks science fiction, and we will not have it tomorrow or in 10 years. But you realize we can make things moving, rotating, translating. We can transport things. This is happening at this moment in our colleges, our universities, our institutes. We are feeling like babies that make the first small steps. But realize in 50 years from now, the doctor might inject a nanorobot in your body that goes to detect a tumor cell at an early stage, or deliver a drug at a very precise precision. I'm not very good in prediction. I'm a scientist. So I want to use this quote: the best way to predict the future is to invent it. And this is what we do in the academic communities, in our institutes, together with our partners in industry, etc. So, the perspective to the future is, I showed you, we start with Mother Nature. We look at the flying bird or the motion in your body, and we try then to design switches and motors. That is what I shared with you today. And in the future, we will have many dynamic systems, bringing dynamic functions and motion to our world. Smart drugs, responsive materials, molecular machines that can operate like maybe soft robotics, etc. There are lots and lots of things to invent, especially for the younger people here. Don't worry. There are tremendous opportunities to discover, to learn, and to invent. I couldn't have done anything, wasn't it, for the young stars that are in my team. The students, the undergraduate, the graduate students, the PhDs, the young researchers. We have a big team, and we share a passion for science and knowledge, and to invent our future. And I hope you share with me this passion, being here at one of these famous universities, the Comenius University. The passion to develop our future. Don't worry, there's a lot of opportunities. And if you doubt, let's not forget the words of Leonardo da Vinci, who mentioned 500 years ago, when nature finishes producing its own species, man begins with the help of nature to create an infinity of species. Opportunities for the future, and for the young people here in the audience, the young students, imagine the unimaginable. Thank you once again for the great honor, and thank you for the opportunity to be here today with you. Thank you so much.